Now, so get out your notebooks, and we are on page 63 here. And let me go to the document camera. And so we can start part 5, chapter 16 on multiple regression. So, what are we doing today? What we're doing right now is we are going to be predicting a quantitative y, a single quantitative response variable y. That's what we've been doing so far. But now, instead of having a quantitative x and a binary y, like we're going to have two quantitative x's. So, just to repeat, I see some people coming in. We're starting multiple regression today with two quantitative x's, two or more quantitative predictor variables, predicting a quantitative y. So, for example, we haven't done this yet. For example, in this example here, we're going to have homework and exams. This will be our x1 and our x2, predicting a y, the final. Now, if you recall, earlier, we looked at just exams, the 3 midterm exams for 107 students from a former Stat 100 class. We saw how they predicted final. That was back on page 29. Now, when we started simple regression, now we're going to add homework to that. And we think we can make a better predictor, better prediction. All right. So the first thing that I want to point out is that the slopes in the multiple regression are not the same necessarily as those in the simple regression. We saw that before with the binary and the quantitative variables, x is predicting a y. It's the same way here, and so we're going to examine that some more. So we're going to expand on that simple regression example. We used exam averages to predict final exam scores, but we're going to use a slightly different data set. We're going to use the unrounded numbers here. So if you want to look back, that was on page 29, where we just did the exams predicting the just 1x predicting the final. Now, we can look at this table here, and it shows the exam averages, homework, exam, and final, averages and standard deviations for a group of 107, that's n equals 107 students. And we get this correlation coefficient, capital R, that we haven't really explained what that is yet. Because so far, correlation coefficients are only defined on two sets of numbers, right? As, for example, for this 107 students here, each student we would convert to a z-score. If their student was exactly at the average, for example, for exams, the z-score would be 0, all right? Maybe I should show you the formula in more detail. That's in the back of the book here on page 151. We're just looking at this formula here, where we take your x and your y's, and we change them into standard units, unit-free. So even if we were in different units, like one was height and one was weight, we find this common measuring stick that basically just tells you how many standard deviations you are above or below average. So we do that for all the points. In this case, it was what are we talking about? Well, whatever two variables we're talking about. And you get z-scores that are unit-free, this common measuring stick, and then you just take the product. For each person, if there were 107 people in the data set, you just take the product of the 107 z-scores, and then take the average of those. That's what we do for correlation. So now, but that's only defined on two sets of numbers. So what do we do when we have 107 students, each with 3 numbers associated with them? So, well, for multiple regression, we define R as the correlation between two sets of numbers, but they're the sets of numbers between people's actual y's, their actual finals, and their predicted y's based on the multiple regression equation, based on that. Like that would be homework and exams predicting final scores. So the correlation between their, if we converted between the y's predicted and their y's, their actual y's. All right? That's what it's defined as. Now, so let's write, that's right here. And now I want to distinguish that between there are three simple little r's involved here. What are they? They're the r between, remember this is y, so this is r between y and one of the x's, x1. This is r between y, the final, and the other x predictor. And then the last one is what? It's r between what? What do you think? x1 and x2. So you have three simple regression r's that are not the same as this r. Okay? Any questions? For simple regression, it is the same. The r is positive. It's the absolute value of those two things. You can compute them either way. You could compute it as this, or you could compute it the same way as we just said, the correlation between your actual y's and your predicted y's, but it's always positive here. And that makes sense, because you're not going to have your predicted values, by definition, are trying to get close to your actual values. They're not going to be oppositely related, so they'll always be positive. All right, now let's turn the page. So now we're on page 64 here. And let's take a look at the two predictor variables separately, like we did for simple regression. So let's look at the two, just simple regression. Here we have our y variable, and we have x1, homework predicting y, and here we have exams predicting y. So this is like x1 predicting y and x2 predicting y. And we see that both scatter plots show a positive trend. They have different correlations. This one has a correlation of almost 0.4, homework's predicting final, and this one has a correlation of almost 0.6. Are you surprised that this one has a stronger correlation? We're predicting finals from exams predicting final. Don't you think that's going to have a stronger correlation than homework predicting final? I mean, final is a type of exam. So if you have very good exam skills, it makes sense that this would be more correlated than homework and finals. Agreed? All right. So now, what's the point of combining these two into a multiple regression equation, which is what we did right down here? But what is the point? Why would we want to do that? Well, obviously, we can predict final exam scores better if we're combining information from two predictors, right? But why not just use them separately? Why not just use them separately? And one reason is that when we combine these two predictors into a single multiple regression equation of this form here, what we can do is we can look at the effects of each predictor while controlling for the other predictor. In other words, we can separate out the effects of how much of this slope is due to homework and how much in predicting finals, when we do this, we can say, we can partial out the effects of the other variable. We can say, okay, controlling for exams, just looking at people who have the same exam scores, how much difference does homework make? We can stratify. We can stratify on that variable exams and say, okay, for people who have 70s on exams, how much difference does my homework make? People have 80s, and that's what this is. And same for exams. We can control for homework. So we can say, okay, for people who have the same homework score, for people who all have like a 90 on the homework, this says that each extra exam point on the average raises your final by 0.5824 points. Whereas this one says for those who have the same exam scores, let's say 90 or 80 or any of it, because it's forcing these parallel slopes. So it says given the same exam score, just look at people who have a 90 on their exams. How they both have 90 on their exams. How does 1 point difference in their homework affect the finals? Well, on the average, it's this effect. For each extra point on the homework, it on the average raises your final by 0.1641 points. So clearly the effect is stronger. Now, why didn't we get the same exact effects as we got here? I mean, when we put a multiple regression, why didn't we say, oh, this is how much for each extra point on your exams, your final gets raised on the average of 0.6647. Why is it less here? And same here. This is saying when you ignore, when you lump this is lumping, paying no attention to exams. It's saying just lump everybody together. You're not controlling. You're not comparing apples to apples. You're not stratifying. You're just lumping everybody together here. And it says for each extra point of homework, your final exam score on the average goes up by 0.3436 points. Can anybody figure out why those all of a sudden are both diminished when we put them together? When we put them together and we control for them? Do you notice do we have the same slopes? No, they're less. You can see they both went down. Compared to in the simple regression. Why did the slopes change? Well, the key to that is looking at the next page here, is looking at that third graph, how homework and exams are related. They are correlated. Homework and exams are related. They have a correlation too. So part of the effect, why do the slopes change? Because the two x predictors, x1 r between x1 and x2 is not equal to 0. Homework and exams are correlated with each other. So, I don't know if this visual helped. It helped some people before, but imagine you have homework predicting finals, and then you also have exams, but if they're correlated, think of their predictive value as being overlapping. Exams predicting final. So you have this little correlate right here. So the separate ones, when you combine them, you'd be almost part of the, if you look at this, part of this effect of homework is because people have higher homework scores also have higher exam scores. Same here. People who have higher exam scores also have higher homework. So when we separate them out, it's looking at it has these slopes are called partial slopes. After you partial out, remove the part that's due to the correlation between homework and exams, that they're predicting the same. Part of them are predicting the same thing. Are mixed together. They're mixed together, so you separate them out. And if they're correlated, then those slopes are going to, in this case, go down because everything's positively correlated, but they're always going to change. They could go up. Okay, So let's read this and we'll go on with this idea in a minute. All right, so they change because they take into account how the homework and exam averages are correlated. Now here's a what's called a correlation matrix, showing how all three variables are correlated. And in the multiple regression equation, we have to take all three of these correlations into account. First, how are you going to read this? This is x1, x2, and y. x1, x2, and y. And these are our correlation coefficients. First thing you notice in all correlation matrices is down the diagonal here is all ones. Why is that? Why is that? Let's just go. I'm just curious. How many people, I'll just do an iClicker question. Okay, so let's just quickly go to the, first we have to write down, why do you think these are correlated? Can you look at this and see why? What am I doing here? I'm saying homework is correlated with homework. X1 is correlated with X1. X2 is what's the correlation between X2 exams and exams? If I know your exams, can I perfectly predict your exams? Do you see why this is all one? Do you? Do you understand why that's all one across it? Because the correlation between X and itself is always going to be 1. If I know your exam score, I know your exam score, right? All right. How about now? The next question is, do you notice any symmetry here? Look at the symmetry. There's really, see these three numbers? See how they're exactly the same as those three numbers, right? Why? Why is that so? Do you think it's because so for example, this and this. Let's read what it says. This says that x2 is correlated with x1, and this says x1 is correlated with x2. So see how the diagonals are all the same, because why? So diagonal is 1 because why? X, because the correlation between X and itself is equal to 1. Now, the off diagonals, the off diagonals are equal, are symmetrical, because what? The correlation between X and Y, or X1 and X2, is the same as the correlation between Y and X. Does that make sense to everybody? Does it? All right, time for an iClicker. I just want to see if it makes sense for everybody and get an attendance grade too when you come in. So let's just do that. All right. So, does it make sense to you? A, yes. You understand the correlation matrix, say A. If you don't understand the correlation matrix, say B. If you're not sure, say C. A, B, or C. Understand the structure of the correlation matrix. A is yes, B is no, and C is not sure yet. Okay, it's just this. I'm just going to let go till 40 seconds, because you should be able to do it by then. Okay. Good. So most everybody understands. All right, so now we're going to go back to the PC. All right, so now, okay. So here, as I said, is a scatter plot relating the two. This is like x1 and x2 here. This is like x1 and x2, whereas the other ones were, as you recall, I didn't put it in, but this is x1 predicting y, the final, and this is x2 predicting y, the final. So now there's three. When we get those multiple regression equation, we have to consider not only these two, but this one as well. And here we get another regression equation. And just to remember how you get this, let me just, in case you forget, how are we getting this slope here? What we're doing is we're saying, okay, the slope for all of these slopes, how are we getting them? It's the correlation coefficient between homework and exams, that right there, 0.3933, that 0.3933 times what? The ratio of the standard deviations, SDY over SDX. And in this case, Y is going to be the, excuse me, in this case, Y is going to be the exams. So we want times the ratio of the standard deviation of the exams over standard deviation of the homework. And we saw that on the first page, right? So standard deviation of the exams is 9.197, and of the homework is 11.73. So let's write that in, just to make sure you know how to do this. And that's where you get your slope. All right. Now, let's focus. First, I want to explain why, when you have a correlation between your x variables, why and how, exactly how, the slopes change. So let's focus on the homework slope, okay? We had a homework slope on the previous page, right here, this homework right here, of 0.3436 that changed when we went to the multiple regression. It changed, it went down quite a bit. And what I'm saying is it went down because of the correlation. Think about it, if it wasn't exams, but something that was completely uncorrelated with homework. And, for example, let's say you had two people grading the final, all right? And one person just added 2 points to everybody's score, completely unrelated. They randomly were 107 students, randomly divided to be graded on their final between two people. One person was an easier grader and for some reason just added 2 extra credit points, all right, to everybody's score, or just did that. So you could say, you would have, pretend they were completely uncorrelated. So this would be your homework, just due to the homework, the correlation between how people did on the homework and how they did on the final was about 0.4, and we got this equation. And then, of course, there would be another variable, not called, that would just be a binary variable. Just to give you, pretend that it looked like this, and it was just the binary variable would be what? The grader, just 0, 1 if you had predicting the final. So if you had the easy grader, you got 2 extra points, all right? So it would be just, the effect would be your final would be equal to some intercept, which should just be the average, plus, the average without the 2 points, right? And then you'd have plus 2 more points depending on which grader you had, and that would be a 0 or a 1. So you'd have that slope for grader, and you have that. Now, if you combine them into a multiple regression equation, these are completely uncorrelated. So you could just say final equals this, 3.436 times homework, right? Plus, and that's how your homework, and then depending on whether you happen just by the luck of the draw to get that good grader, the easy grader, plus 2 extra points for the grader, 0 or 1. So you'd either get this, this score or this score plus some, this is predicted final. Of course, there's a lot of error. Predicted final plus some intercept. And they wouldn't have to change them. They're completely uncorrelated. They have nothing to do with each other. But the problem is, when they're correlated, what each one is doing is saying, okay, after I, for example, make this after I predict everything, after I make this prediction, I have these errors left. And it's saying how much of these errors can be explained by the exams, but not the exams that are correlated with homework, the exams that are also residuals left over that aren't the same thing as, that aren't predicted by the homework. So it's basically, that's what you're doing. You're doing another regression on these residuals with these residuals. Does that make sense? All right, so that's what we're doing. So we could do it through matrix algebra, but how many of you, another eye clicker, I want to know how many, because I am planning, I need to know how to teach this, because there's a huge range of people in here. So another eye clicker, before I forget. Yes, if you've had linear algebra, any linear, matrix multiplication is all you need. Inverting matrices, stuff like, no calculus, you don't need that. So, yes, if you've had matrix manipulation, so you know how to take the inverse of a matrix, you know how to multiply them, all that stuff. Yes, no, if you don't know that. Because this is very easy if you know matrix multiplication. But I want to see how many people do know that. So A, if you've had matrix operations made like a linear algebra course, like here, 125, 225, 415, any of those. All right. And no if you haven't. Or if you don't feel comfortable with it. No if you don't feel comfortable. Okay, so I just want to see where people are at. Okay, I'm going to stop it. And let's see. Half and half. All right, so it's worth doing something, but it's not going to be required of everybody. So I'll just, side by side, do a little, do the same thing, not here and now, but as a supplement, because half of you are just going to be mystified if I do it here and now, as a supplement. Okay, very good point. Thank you. Now I'm going to go to the document camera again. All right, so instead of doing, look, we only have two variables here, two x's, so I can do a very simple matrix multiplication. And those of you, even who haven't had it, might want to look at it. But I'm going to do the same thing here the long way, all right? In an intuitive way, actually, much more intuitive probably for you guys, for everyone. All right, so what am I going to do? Let's focus on this homework slope right here and how it decreased from 0.34, this one, to that. Okay, here we have it. So what I'm trying to figure out is why this changed to that. Let's derive that. Now, it's easier, just much simpler, actually with matrices too. You don't have to do any inversion. If you go from this direction to this direction. So that's what I'm going to do. I'm just going to show you how you get from the multiple regression to this. And the way that we're going to do it, it's really, really simple, you'll see, is because we want to get rid of these exams and change this to something in homework. And if exams and homework are correlated, you have an equation to do that. You have exams equal, right here, you have that. So you can replace, we want all of this to be in homework, and you can use that, the predicted exams. All right, so instead of writing exams, we are going to put right inside here, what? Let's forget about the intercept. We're just trying to get the slopes here. So we are going to put right in here 0.3083 times what? The homework. Now, all we have to do is add this plus that times that. So you're saying, okay, when you separate it out, when you partial them out, this is the part of the final that's explained by the exams, right? But now when you smush it all together, if you want to put them all together, well, the exams are also correlated with the homework. So part of that, this part of it, is going to also be could be expressed as due to the homework. And if you say this plus the product of that will equal that. It's just super easy. So that's what we're going to do. And we'll do that on the next page. I could do it right here, but that's exactly what we're going to do. We're just going to say this times this plus this will equal that. But this is just more explanation of what the slopes do, what it means to control for the other variable. All right? And we did this, we've done this a lot. It's exactly what we did before. We just looked at, controlling for gender. Remember, we just said, what does the effect of your shoe size have on how many pairs of shoes you have just for people of the same sex? And we even did it for the quantitative variable. We said, okay, for everybody with a size 10, what difference does gender make? And that made a huge difference in the number of shoes people buy. So now we're just doing exactly the same thing here. For everyone who scored an 80 on the exams, an extra point in the homework will increase their final score by that. So it's controlling for the exams, saying you have the same exam, get that out of the picture. What extra effect does homework have? And same here. Get the homework out of the picture. What extra effect does the exam? And that's the whole point of multiple regression. Here's another way to think of it. After you predict finals from exam averages, how much more can we improve our predictions by adding homework in, and vice versa? So the question is, we just answered it before, when would the coefficients of the two separate single regressions be the same as the ones of the multiple regression? We just did that when we looked at these two examples. If you have something that's totally uncorrelated, like the grader had nothing to do, it was randomly, had nothing to do with the homework. So then it would be, when the correlation between x1 and x2 is equal to 0. Then you could have this picture. I don't know if this picture helps you. It's just a sort of intuitive picture. And then you would have, like, for example, homework and exams. This is the explanatory or the predictive value of these two, and they're not correlated with each other at all. They have nothing to do with each other, like the grader and the homework. That would be a better example, because these do have a correlation. So it would be like, okay, which grader you get, the easy grader or the hard grader? And that has an effect on the final. That adds 2 points to the final. And this has an effect on the final, and they don't overlap at all. So you would keep the same they're not correlated with each other, so you would keep the same exact slopes in the simple regressions as you do in the multiple. All right, I'm just going to do exactly what you have a homework problem like this, and some people wanted me to work it out in more detail, so let's do that. So how do you go from a multiple regression to a simple regression? So you're going to start with this full model here, right? And what do we want to do? The full model has homework and exams. And we want to get to the simple, just plain homework. So what do we want to do? We want to get rid of this exams right here and replace it with what? Homework, right? That's just what we did. So to get to the simple, we want to eliminate exams, and replace it with homework, right? And how do you do that? Through that equation that we just looked at, the previous page. We want to get rid of that. Well, predicted exams, are equal to that plus some intercept. So we're going to get rid of that exams and replace it with this. Now we have just one coefficient here, that other one, plus the product of those two. Okay, and that's what we have right here. And then when we add that together, 0.1 plus that product together, this together equals that. Now we add those two pieces together and we get this. So it's pretty simple. I think you should read all this for understanding, but sometimes when I read too much or say too much, sometimes it's confusing. It's better for you just to read slowly on your own. I think I explained it. This is for you to go over. It's just saying the same thing I've been saying over and over again. And now if we wanted, we can go in the other direction. We can say, okay, so what do we do here? We got that simple equation. Now let's get exams. So now what do we want to eliminate? We want everything in terms of exams. So we want to eliminate this and replace it with something as exams. All right, so how are we going to get that? So let's just write this down. One, our first step, just like I did in the previous one, just go through the same steps. Our first steps is we want to eliminate homework. Okay, we want to eliminate homework. So we need some equation that's what? Homework expressed in terms of exam. Predicted homework. You can't just switch around the other equation because they're not usual equations. This is a predicted. They have error attached to it. So now we want homework equals something times exams. The regression of y on x is not the same as x on y because these are not just your usual equations. They have predictions and error attached to them. So we have this plus some intercept, right? And so that's what we want. We just need this part. Plus an intercept doesn't really matter. We're not concerned with that, this. So what do we need to do? So we better get the slope there. That slope is r between homework and exams times the ratio of the standard deviations of y over x. So this case, y is homework. So it's going to be exactly like what we did before, but here we have exams. So now we're just going to have that same correlation, but instead of having, see here, exams was y. So don't you think we should just flip those two? Does that make sense to everybody? This is the standard deviation of exams over homework. We want the standard deviation of homework over exams. So let's just do that. R is the same. Correlation between homework and exams and homework is the same. But now, so we're just going to say 11.73. That's the standard deviation of homework over 9.197. And I got 0.5016. 0.5016. And so that's right here. That homework is going to be replaced with 0.5016. That's going to replace homework. Because that's what homework is. So we're going to put that in there. All right, so let's just do that. And we get final equals 0.1641 times what? Times that. Times 0.5016 times exams plus 0.5824 times exams, that doesn't change, plus the intercept. So we get this, excuse me, I don't want exams squared here. I just want, oh no, this is right, this is separate. Okay, I'm good. I want these two multiplied together, and those two multiplied together are 0. It's about half of that. So it's 0.0823 times exams, plus, then I'm going to add that part, 0.5824 times exams, plus the intercept. And if I add these two together, I should get that. Okay? Let's add another sheet of paper here. Just to go down, you can fit it on yours. I'm just saying equals, I'm just going to say this plus this is 0.6647 times exams plus an intercept. Just this plus that. Does that make sense? Does that make sense? The intercept is just that the intercept we're not worried about. The intercept's going to change, but we're just interested in why the slopes change. Does that make sense? So these two, that's what I got. These two together equal that, which is what I wanted to show. Does that make sense? Why is this hard? I see. Okay, iClicker question. Do you understand this or not? Did you understand? Would you be able to do this calculation? I'm just doing it on an iClicker. Another one. Okay. Did you get, because I see puzzled faces. Yes, I understood that calculation. No, I didn't. Because you're going to have to do it on your homework. Yes, I did. No, I didn't. Yes is A. Yes, I understood. No, I want you to spend more time on it right now. You want another option? You don't know? All right, so I'm going to stop it. Let's see, just vote. Okay, let's see. Whoa. Okay, so most people understood. I think the other ones will understand if they think about it. So let's move on. All right. If you want a prettier look at it, here it is on the other notebook I did in the other class. This is what it looks like. And I just added that together with that and got this. It's exactly the same thing I just did. It's just this last line looks pretty up here. All right. Now, let's go ahead. And this is our summary. And let's see if there's anything we need to highlight on here. All right. So multiple regression with no interaction terms. We have no interaction terms right now. Looks like this. When we add interaction terms, we're going to have to multiply some of these x's together. That's an interaction term. So far, we're assuming that the effect of, we're assuming parallel slopes. And we're going to look at those. That's what we're going to do in our next chapter. If different x's are correlated, the coefficients are not the same. We just saw that. The slopes in the multiple regression are called partial slopes since they quantify the effect of each x variable and their response variable after the other x's have been partialed out or controlled for. We saw that. What predictive value do they add after you've already accounted for the other variable? And here, this is what we're going to be looking at right now. We're going to look at how it forces, without an interaction term, it's going to force all the variables in the model to have the same slope for all levels of the other variables. In other words, the effect of homework will be the same whether you got a 90 on the exam or a 60 on the exam. That might not be true. The homework might help people more who get 60s on the exam in predicting finals. I think it probably does than people who it might have a different effect, in which case you have to add an interaction term. But multiple regression without it just means, okay, it's going to have the same effect. Those partial slopes, you say, assume that they're going to be the same for all levels of the other variable. And then it's a nice way to separate the causal effect of one x from another, from the confounding effect, because you're separating out that confounder. You're saying you're looking at just the same level of what everything is a confounder and see what happens then. So it's a very nice way when you're talking about causation to assess whether there's causation or not. And then this last thing is, okay, so we said if the x's are correlated with each other, then the slopes are going to change in the multiple regression. But we didn't talk about the danger of what happens when they're completely correlated or very, very highly correlated. If two predictor variables, this is important, and we haven't talked about it yet, if two predictor variables are highly correlated, you don't want to put them both in the model. Here's a good example of it. Let's say you're trying to predict height from your right foot. Your right foot is a very, very good predictor of height, right? And adding your left foot isn't really going to help you very much. But if you do, if you put those both in there, then almost, since they're predicting pretty much the same thing, very strange things can happen. You could easily get one is significant, like maybe, for example, but if you put them both in the model predicting height, either one, and sometimes even both of them, can end up non-significant. Think about it, like if you get all the predicted value from let's say your right foot, adding the left one in, well, that could come out as not significant. That doesn't mean that it's not a good predictor on its own. It's only your right foot. You just get screwy results because pretty much they're predicting the same thing. So almost any linear combination of the two of them will be just as good. So what you're doing is you're just fitting to some particular random errors in the model and not to really the predicted value of the two. It's very sensitive to just sort of random noise within the model, which linear combination of the two things it happens to choose. So it's really stupid to include two things that are, I mean, you know that with feet and height. You would never do that. But lots of times you're, unfortunately, looking at models that you don't understand very well and not thinking about or don't know what their effects are and so then people can do silly things like that. So what people do to avoid that, and what you should always do, is look at the correlation matrix and make sure they're not super highly correlated with each other, any of the two variables. All right, now, the next part, what I'd like to do is give you a visual, finally. So many people are visual learners, I am, and so let's just try to picture all this. And particularly, let's see what happens, what we mean by these parallel slopes and no interaction terms here. So the slope for each predictor variable in the model controls for the other variable. We're interpreting the slopes in the multiple regression model. Think of it this way. We have observational data. The high and low homework groups are not balanced. Those with high homework also have higher exams. The higher final exam scores are partially predicted by the higher homework scores and partially predicted by the higher exam scores. The slopes in the multiple regression equation are called partial slopes since they quantify the effect of each variable after the other one is partitioned out, partialed out. Basically, it's this equivalent of stratification. You're looking at or controlled for. It's really stratifying on the other one and saying, okay, for all the different levels, let's see what's going on. So the homework slope in the multiple regression describes the effect of homework on finals for those with the same exam scores. Same. Okay? For those with the same exam scores, the predicted final is 0.1. This slope says that for those with the same, if you have all the same, exam scores, for those who have 90, the predicted final score is 0.1641 points higher for each 1 point increase in homework average. And here's how you can see that. So for example, here I just have homework, predicting final. And I want to explain this slope here, right? That's what I'm trying to do here. Just explain this slope. And what it does is it controls for the exams here. And here's how it does it. So think about it. We just have this homework predicting final. Instead of having this big slope that goes across here, like we did before, what was it? Almost 0.4, we don't. We have these little slopes. Why? And the idea is this, that you say, okay, for those, because you can stratify. That's what this allows you to do. It says for those with people with exam scores equal to 90, your final is equal to 0.164 times your homework, this slope, homework versus final. This slope, 1 point in homework, you only go up a tiny little bit in final, but then the intercept changes here. For those with 90, the intercept, you add the 11.91 to 0.5824 times 90. So you put a 90 in for there. So you'd have 0.5824 times 90. And then you'd add this. So, and then for 80, you'd say 0.5824 times 80. So it's a drop. And it's a drop of, since we're going down 10 points, we're going to drop down 5.824 here, plus 11.91. And finally, it's going to be the same here, 0.5824 times 70. Plus 11.91. So you get these three equations like this. And if I wanted to, I could simplify it. And this, the slope is the same in all. See, these have these slopes that are the same. And all these lines here, all these lines are parallel because of that. Parallel. See? They're all parallel. They have the same slope there. But their intercepts are different, and their intercepts are different because we're plugging, So what is this intercept? Boiled, if you add these two together, all that together, we get, this is going to be the intercept, plus 64.326. So if they didn't do any homework, people with a 90 would still have a 64.326. That's our best guess. If they didn't do any homework, but they only had an average of 80 on the exams, then it would be plus, we'll multiply, 58.502. It's just, what is it? Since I dropped down 10 points, I'm just saying 10 times 0.5. So it's this, the difference, this, if you subtracted 5.824, you should get that. And if I subtract another 5.824, I'll get the next one, which is this. And that is plus, this is just the intercept, 52.678. All right, so you get these three equations. And this is when you have the exams equal 90, exams equal to 80, and exams equal to 70. Okay, so there you have it. But that's stratified. And this goes back to our idea of confounders. If we were talking about confounders, okay, we have this stratification. But now, if you ignore, this allows us to stratify on exams by putting exam in there, just like we used to be able to stratify on gender with a multiple regression equation, because we could put gender in here. If we don't have that, then what do we have instead? We have this overall, we have this slope in the simple. This is the slope you see here in the simple regression equation, excuse me. That. It's not distinguishing. It's mixing up all the different exam scores. And why is it different? because they're correlated. These simple exams, what's happening is, look at this. It's fitting these right here. And what are those? Okay, so these are the same equations we have here. Let's just show you. This is just copied. All right, so this is from your simple equation, your simple homework predicting finals, where we're ignoring levels. Now, these are the multiple regression ones. These are the various stratified multiple regression. So these are multiple regression. They're simple in that they're from this multiple regression equation. And they're controlling for the effect of exams. They're comparing people with like exams so you can see what's left. You're not comparing apples with oranges. This is mixing things up. And why does it look like this instead of just like this is because look at this. The people who have the high exams are right here, are way up here. They also have the high homework. See, these are the people with the high exams. They also are concentrated up here. That's why I'm fitting this line here. I'm doing an exaggerated version. The people with the middle exams have the middle homework, and the people with the low exams right here. See, this is the key here. So that's why it looks like that. If they're not correlated, it wouldn't look like this. You wouldn't have it like that. They'd be evenly distributed, and then your overall regression would just be like that. You'd have, okay? So that's the idea. Now, and then you get this different slope that's much stronger than that one. That's our pill. In keeping with that, why don't we see where this fits into the plane? So let's visualize this on page 72 and look at the multiple regression scatter plot. Okay, so this is on page 72. So each of the 107 students has 3 scores. So each student is represented by a point in the 3D plane. So for example, let's look in here, see what's going on. Hold on. Okay, so given their homework and exam scores, we're estimating the final score. The scatter plot shows their final exam score as vertical distance from the point in the homework exam plane. So, for example, this person, what did he get? Like a 40 on the homework and not very good here either. Well, not terrible on the exams. And but he skyrocketed on his final. Whereas this person has this tiny, oh my gosh, terrible. Just a tiny little, this person has a 65 on his homework. And where does this start? This starts at, what is this? The exams. It starts at 50. Okay, so that's 50, 60, 70, 89. Okay, so this person right here has a 50, 60, 70. Okay. And boy, did he bomb the final. He only got a 40. That's sad. Okay, so now what we're trying to do is so these are the actual final scores of people given their homework and their exam scores. So this is their actual final scores. And what we're trying to do is fit a plane that best, these points don't all form a plane, right? We can't, but we're going to try to get the plane that minimizes the sums of the squares errors. So multiple regression, whoops, I gave it away. In multiple regression, we're looking for the best fitting, I just said plane, through the y so as to minimize the squared errors of those finals. And you can see here I fit a plane right here that does the best job. Here's a picture of the regression plane. It's the It's a plane that minimizes the sum of the square errors. So it's a plane in 3D space. It's in the scatter plane, no, in the scatter space, whatever you want to call it. So the scatter, we're fitting the best plane in 3D space. All right, now let's look at those slopes that we got, okay? So let's just do that now. And we got, what did we do here? We looked at the exams, and along here is the homework, and here is the exams. This gradual tilt, look, see how the slope of the homework is the tilt of the plane? As you go from 30 to 100, that's that gradual zero, that's this. It's a gradual slope, whereas you go for the exam, for the effect of the exams is very steep, okay? So, very steep. So, this is people who got an exam of 100. How about people who got an exam of 90? Let's look at them. There's the people who got an exam of 90. There's the people who got an exam of 80. This is what we exactly just did. 80. And there's the people who got the exam of 70. Right? And those are the 3 parallel lines we just did. 3 parallel lines from page 68. That's what we just did. So for example, so this is 90, this is 90, this is 80, and this is 70. And those are these equations. So for example, our predicted final, we said for this one, they all have the same slope. They're parallel. And this is the homework slope. It's the difference homework makes. People with higher homework do slightly better, but not by that much. But, okay. And so, so this is the homework slope. This should be multiplied by homework, excuse me. Homework and homework. And then we're going to add an intercept, and those are the intercepts we just calculated. We said this one was about 64, 64.362. We said this is about 5 less, 58.302, and this one was another 5.5 left, 52.678. Okay, it was that, that 5.824 less. That's what we've got. Now we're going to do, let's just, do you want to look at the other ones? Here, why don't we turn the page? We might as well just do that, and you'll see in the other direction we can do the same thing. So if you turn to page 69, we can do exactly the same thing. So if we look at page 69, and now we're saying the exam slope describes, okay, so now we're focusing on this, right? And we're saying the exam slope describes the effect of finals for those with the same what? Homework scores. For those with the same homework scores, the predicted final is this much bigger effect. And now we're going to have those other slopes that are all parallel. So let's just do the same thing. For homework 70, 80, and 90, we're going to have a strong effect of almost 0.6, 0.5824, all the way down. And now, how is it going to be affected by changes in the homework? Well, that's given right here. So if you have 70 in a homework, it's going to be 0.164 times 70. Here it will be 0.164 times 80, and here it will be 0.164 times 90. And then it's going to be adding the same intercept. So it's not going to have as strong an effect. When you multiply by 10, it's just 1.64 points. So now we have this part. The intercept will be 23.397. This is all intercept. This is 25.038, and this is 26.679. So why don't we just graph those so you can see? It's the same exact thing, but now they're going in the other direction. So now you look at this plane, right? And this plane, here, I just get this. Okay, so now can you see? All right, I got to get my glasses on. hard for me to see. All right, so I'm talking about, all right, so the exams, all right, so these are the people who got 100 on the exam. It goes down to that. See, you're looking at this plane. We don't want to look at them. We want to start with, let's look at the people who got a 90. So they're 1 over. Those are the people who got the 90. I'm just going to go down to the edge of the plane so as not to get confusing here. Okay. So these are the people who got the 90 when you drop down. These are the people who got the 80. I should have just gone down to here, and these are the people who got the 70. I extended it a little bit. All right. So 70. Homework is 70. That's these people right here. 70. This is 70, 80, and 90. All right. So for homework equals 70, we're going to have what? For all of these, we have that same, I'll just do 70 there, 80 there, and 90 here. And for all of them, we have what? The same strong effect, right, of exams. So these are homeworks, right? Aren't these homeworks? These are homeworks. Okay, so now what do we have? We have the same strong effect of exam, very strong slope. This slope. But why are they different? They have parallel. That's the effect of the exams. But now they have those different intercepts we just figured out, which the smallest one was 23 point. Whoops, the smallest one should be up here, plus 23.397. The next one was 25.038. And the last one was 26.679. Okay. So that's the idea. Now, any questions so far? And these were the parallel slopes on page 69. So we just have two sets of parallel slopes. And these right here are the exams. So homework doesn't make much difference. Exams make a lot of difference. All right, now, what do we have left to do? Let's answer this question here, and then I'll post some homework for you guys. So, the equation for this simple regression is this. Why is the exam slope smaller in the multiple regression? Let's do this as an iClicker question. I'm wondering, this is A, this is B, and this is C. I'm wondering if you can get this. So let's go here. This is a good exam question. Okay, so y'all done voting here? It's just participation, so just participate for this. I just want you to think about, engage your brain so you'll know it on the exam. All right, so I'm going to stop it and see. So the answer was, which one did you write? B, overwhelmingly. Let's see which B, let's make it, wow, that was fantastic. That's your best yet. Okay, so let's see if you got it right. I mean, yeah, you did. So let's go to the document camera. So it is B. Because there's a positive correlation between exams and homework, and they're all positively correlated, so we're in this situation. Homework, exams, predicting final. And we've got this overlap. So they're going to diminish, because if they were negative, it gets very complicated if they're not all positive. But yeah, so when you separately, you're going to have this whole big slope and whole big slope. But when you put them together, there's this overlap that you have to account for due to the correlation. Fantastic. Wow. That's really great. You look at that one. All right, now the last thing, this is pretty hard. We're going to look at interactions now, and we're not going to, since we haven't done interactions, we are in this situation right up here. All right, and I want you to read all this, but here's just the picture we've been looking at. Read all this on your own, of course, but I just want you to look at this picture here, and I forgot to put these in. So, all right, so what are we doing here? We have these. All right, so this is final, and this is homework. And in both these cases, there's no interaction. We are in this situation. No interaction. And here's your parallel lines, and that picture on the top right is this, that we have correlation here. We have correlation between your homework and your exams, between the two x variables. If we didn't, it would just look like this. The high exams that look like this, and the low exams, where most of the people on the bottom, a bottom pyramid, and a lot of people have the high exams and the low exams would be the same as the overall here. And you'd have so this is no correlation. So no interaction and no correlation. So correlation between the two, x1 and x2, homework and exams is equal to 0. Between x1 and x2 is equal to 0, and there's no interaction. Predictors uncorrelated, and no same slope, so you get the same slope here. And there's also no interaction. Where can I put that? And no interaction. Now, this whole row doesn't have interaction. I have to add another one here. This has no interaction. Don't even think about this one yet, because we haven't talked about interaction. So we're just right here. So no interaction here either. Okay? But this one is like, okay, look at this. This could confound a causal relation interpretation of a simple slope. This is your simple slope. Simple slope of homework predicting final. These are your multiple regression ones. Let's color them. These are the multiple regression ones, stratified. They're derived from our multiple regression equation. They're simple only because we stratified them. All right? So it's just exactly like that other picture. And this, our simple slope, is the same as them. All right? So this is our simple. And here we don't have confounding because there's no correlation at all between them. That's our simple, not slope, but simple equation. Simple regression equation. That's the simple regression equation. These were the multiple ones stratified. They're stratified how? For people with high and low exams. Multiple ones stratified, controlling for these. You see what I'm saying? So these are the same, but this simple one's a great, because there's no confounding, there's no correlation. This one's a great, agrees with it. This one doesn't. So what multiple regression does is take away that confusing, when you have correlated variables, you want to like get rid of that and see what's going on. And sometimes we have to add an interaction term. We'll do that. We'll look at that later. But for now, that's what we have. Okay, so